The Ford-Fulkerson method or Ford-Fulkerson algorithm is an algorithm that computes the maximum flow in a flow network. It is called a method instead of an algorithm, as the approach to finding augmenting paths in a residual graph is not fully specified, or it is specified in several implementations with different running times. It was published in 1956 by L. R. Ford, Jr., and D. R. Fulkerson. The name Ford-Fulkerson is often also used for the Edmonds-Karp algorithm, which is a specialization of Ford-Fulkerson. The idea behind the algorithm is as follows. As long as there is a path from the source to the sink, with available capacity on all edges in the path, we send flow along one of the paths. Then we find another path, and so on. A path with available capacity is called an augmenting path algorithm. Let be a graph, and for each edge from 2, let be the capacity and be the flow. We want to find the maximum flow from the source to the sink. After every step in the algorithm, the following is maintained. This means that the flow through the network is a legal flow after each round in the algorithm. We define the residual network to be the network with capacity and no flow. Notice that it can happen that a flow from 2 is allowed in the residual network, though disallowed in the original network. If and then. Algorithm Ford-Fulkerson inputs given a network with flow capacity, a source node, and a sink node output computer flow from 2 of maximum value for all edges, while there is a path from 2 in, such that for all edges, find for each edge. The path in step 2 can be found with, for example, a breadth-first search or a depth-first search in. If you use the former, the algorithm is called Edmonds-Karp. When no more paths in step 2 can be found, will not be able to reach in the residual network. If is the set of nodes reachable by in the residual network, then the total capacity in the original network of edges from to the remainder of is on the one hand equal to the total flow we found from 2, and on the other hand serves as an upper bound for all such flows. This proves that the flow we found is maximal. See also max flow min cut theorem. If the graph has multiple sources and sinks, we act as follows. Suppose that add a new source with an edge from to every node, with capacity, and add a new sink with an edge from every node to, with capacity. Then apply the Ford-Fulkerson algorithm. Also, if a node has capacity constraint, we replace this node with 2 nodes, and an edge, with capacity. Then apply the Ford-Fulkerson algorithm. Complexity. By adding the flow augmenting path to the flow already established in the graph, the maximum flow will be reached when no more flow augmenting paths can be found in the graph. However, there is no certainty that this situation will ever be reached. So the best that can be guaranteed is that the answer will be correct if the algorithm terminates. In the case that the algorithm runs forever, the flow might not even converge towards the maximum flow. However, this situation only occurs with irrational flow values. When the capacities are integers, the runtime of Ford-Fulkerson is bounded by where is the number of edges in the graph and is the maximum flow in the graph. This is because each augmenting path can be found in time and increases the flow by an integer amount of at least a variation of the Ford-Fulkerson algorithm with guaranteed termination and a runtime independent of the maximum flow value is the Edmonds-Karp algorithm, which runs in time. Integral example. The following example shows the first steps of Ford-Fulkerson in a flow network with 4 nodes, source and sink. This example shows the worst-case behavior of the algorithm. In each step, only a flow of is sent across the network. If breadth-first search were used instead, only 2 steps would be needed. Notice how flow is pushed back from to when finding the path. Non-terminating example. Consider the flow network shown on the right, with source, sink, capacities of edges, and respectively, and in the capacity of all other edges some integer. The constant was chosen so that We use augmenting paths according to the following table, where, and note that after step 1 as well as after step 5, the residual capacities of edges enter in the form, and, respectively, for some. This means that we can use augmenting paths, and infinitely many times, and residual capacities of these edges will always be in the same form. Total flow in the network after step 5 is, if we continue to use augmenting paths as above, the total flow converges to, while the maximum flow is. In this case, the algorithm never terminates and the flow doesn't even converge to the maximum flow. Python implementation. Class edge. def__init__self.source equals u self.sync equals v self.capacity equals w def__repr__. Return %s to %s %s class flow network. def__init__ self.adjective equals self flow equals def_add_vertex self.adjective vertex equals def_get_edges. Return self.adjective v def_add_edge. If u equals v, raise value era edge equals edge reg equals edge edge.reg equals reg equals edge self.adjective u append self.adjective v append self flow edge equals 0 self flow reg equals 0 defined_path. If source equals sync, return path for edge in self.get_edges. Residual equals edge.capacity, self flow edge, if residual greater than 0 and edge not in path. Result equals self.find_path if result equals none. Return result def max_flow. Path equals self.find_path while path equals none. Residuals equals edge.capacity, self flow edge for edge and path. Flow equals min for edge and path. Self flow edge plus equals flow self flow edge dot reg equals flow path equals self.find_path. Return sum. Usage example. For the example flow network in maximum flow problem we do the following.